All right, we can start. We are live. We are streaming through YouTube, apart from Zoom, and the recording will be made available to everyone who's joined us. So thank you very much. We have people from all over the world. We are very happy about organizing this event. It has surpassed all the expectations, especially the interest generated in the community. So we are very happy. Thank you all again for being here. So I'd like to start saying a few words about Trial Labs. We are as the organizers. So basically, we are a machine learning consultancy company. That means that we help other companies create business value by partnering with them and helping them throughout all the phases of their machine learning path, or as some people like to call it, the AI transformation. That means that we are involved since the early stages of R&D product and proof of concept to putting these systems into production and actually driving the business. For this, we are heavy users of open source technologies. So thank you if you are on the open source community. Our work would not be possible without you. The core expertise that we have is around NLP, natural language processing, computer vision, of course, which is the subject of this webinar, and predictive analytics. Especially, we've been doing a lot of work on demand forecasting and pricing for retail. So Trial Labs was founded in 2009. And if I'm not mistaken, we are around 55 people in the team now. These are some of our customers listed here. Mostly on the first years, we've been focusing more on the US market, but we've grown internationally since. And we also have some customers here joining the webinar. So hello, and thank you for all of you that could make it. As you see, we kind of have worked for several industries. We are working from Montevideo, Uruguay. That's our headquarters location. And this is a picture of our team, which I wanted to show you. Way before social distancing was a thing and everyone had to use facial masks. We were so happy back then. But this investment in us working on the Swift for TensorFlow ecosystem would not be possible without all the great work that's being done by our team. So thank you all for making this possible. Now I want to introduce the stars of the show. Not me, of course, I'm just the moderator. I'm the CTO of Trial Labs. But now we have Joaquin, also called Lalo, and Ian, who are both machine learning engineers, have been working with us for a couple of years, and they will be our main speakers tonight. And we have some surprise for you. So some people from Google generously volunteered to help us during this event. And we have Brad Larson from Google, who leads the TensorFlow, Swift for TensorFlow project. And he will be here to help us with questions from the audience in case somebody wants to know something deeper about the project and the future of Swift for TensorFlow. A little bit about how we got here. In Trial Labs, we want to be aware of what's possibly coming in the future. So we have a division we call Frontiers, as in the frontiers of knowledge. And the idea of this division is to kind of learn about the things that might be coming, might not be ready today, but might be ready in, say, 1 year or 6 months. And if those things kind of blow up and are a huge success, then we can be proud of ourselves of making one of the first people who actually were involved in these things. So we designed like several lines of research that we have, one of which was Swift ecosystem for machine learning, which we saw that it had a lot of promise. And then that made it so we could learn a little bit more about that, and that's how we end up here. And with that, I want to give it to Joaquin, who will be our first speaker. But before, I'd like to say that people can, if you want to have questions, if you have questions, you can use the Q&A part here in Zoom or the chat, and we will tackle the questions at the end. For Joaquin and Ian, and also for Brad and other people from Google who want to answer the community questions that we might have. So Joaquin, all yours. I'm going to stop sharing my screen.
Okay. Can you see my slides?
Yep.
Okay, great. Well, hello. If you're watching this, you probably read our article, which we published about a month ago. In the article, we discussed what we thought about Swift for TensorFlow as a way to do machine learning using Swift. And the idea today is to expand on this article by using personal post estimator model and show how the process of building this algorithm was by using Swift for TensorFlow. About 2 weeks ago, we ran a poll to get a feel for the audience. And most of you know machine learning, so I won't be discussing things like what a convolution is. And most of you know Python, so I'll be using Python as a way to explain some Swift concepts. So yeah, let's start. Why did we choose a post-estimator model for the talk? The thing is that it has two big parts. It has a backbone, a CNN backbone, which is quite normal, and it's usually done in Python. But it also has a decoder, and the decoder is just general normal CPU code, CPU-intensive code. And so that's where kind of Python starts to break down. It starts to show its slowness. And that's where usually people use C++, and they end up mixing Python's backbone and a C++ code around it to get something really fast. And we thought that Swift could shine in being a single language to do both parts, to prototype a good backbone quickly and to get the code around it going really fast. So the Personal Lab post-estimator could be a good way to show what Swift could do, and if you could bridge the gap between Python and C++. Oh, okay. So I'm going to start by explaining how the Personal Lab model works. Then I'm going to explain how building it using Swift was like. And finally, Ian is going to describe the results we got, how fast it runs, and so on. Okay, so let's start. Personal Lab, it's a post-estimation model. So it takes as an input an image, and it returns as an output a series of poses, which are clusterized into individual people. So if we overlay the poses on the image, we have several key points, and each key point belongs to a person. And you can see like some sort of skeleton being drawn on each person. That's the network being aware of each person having a certain pose. And it has several parts, which I'm going to describe. The first part of the algorithm is as usual, a CNN backbone. The backbone just takes the input image and compresses it into a more abstract representation. So it converts the image from having numbers, which mean colors, to meaning something more abstract, like a shape or an edge or a body part and so on. And in this case, the CNN produces 4 tensors for abstract representations. The first one is what we call a heat map. And this heat map is just a tensor which has 17 layers. And each layer is trying to predict the probability of each pixel containing some key points, some body parts. So maybe the first layer is trying to predict how likely that in some zone in the picture, we have an elbow or an eye, or an E and so on. And if we zoom in and we just stack them all together, we have like red areas, which indicate high likelihood of containing some key points. And you can see that on each joint and in each part, we have like a high confidence area of containing some of the 17 key points we have on this network. Okay, we have then 2 more tensors which get produced by the backbone, which are the displacement forward and backward tensors. These tensors try to predict the displacement between 2 contiguous key points. So for example, they try to predict if I'm standing on a knee, they try to give me a vector which would take me to the ankle or to the hip, because they're together. And if we zoom in, it looks like this. So each key point has a vector trying to predict the next key point. And we have two tensors for this function. We have a forward one and a backward one, because we can parse the pose going from the nose outwards, which would be forward, or from the nose inwards, which would be backward. So each tensor could take us forward with regards to our pose, or backwards with regards to our key point, or backwards with regards to our key point. Okay, we have then the final tensor, which is just the offset tensor. This one is quite simple. It's just 17 layers, with each layer trying to predict the center of each key point. So we have several key points which take an area. So maybe the elbow takes a certain area, but we want to get from an area to a very specific point. So each pixel on this joint is trying to get us further towards its center. So it just predicts a series of vectors, of very small vectors, which just try to get us closer to the center of each key point. And it's 17 layers, which is actually 34, because we have an X and a Y components. So it's 34 layers for 17 key points. Yeah. Okay, so we have these 4 tensors. We have to somehow get them to give us poses which are clusterized in different people. And for that, we use the decoder. The decoder is quite simple. It starts by just taking our heat map and then just going to each pixel in the heat map and trying to find out if the pixel is locally maximum. So it takes a radius around each pixel, sees if it is maximum, and it stores it. So we convert this heat map into a list of locally maximum possible root key points for our poses. And it looks like this. We have like several, candidate key points to being a real key point in a real pose. So, the heat maps are not Gaussian, so we could have several candidate, several maximum key points on each part. And maybe some of them are noise like these ones, but yeah. So we have a list of key points, which could be, part of a pose, and we just sort them with regards to how confident we are that they are actually a key point. And then we just take the maximum one, the one with the highest confidence, and start predicting our pose, our first pose, from our maximum key point. And that one, let's say we have that this one is the maximum one. Okay, so we go there. 1 second. Okay, so this is the first key point. We go to this XY coordinate into our displacement tensors and find the displacements to our next and to our previous key point. So maybe we have that the next key point, the next vector takes us towards this point here. And maybe the previous one takes us towards here. So we just went to the displacement tensor. We just went to the XY coordinates and to the correct layer, which has the correct, displacement. And we got 2 different vectors. But we can see that they are both kind of inaccurate. They aren't really taking us to the correct ankle or to the correct hip. So we can just then go to the offsets matrix, go to the correct XY coordinate, to the correct layer, and get 2 offsets, which are here. And they take us further towards the correct point, which marks, the joint or the hip. So now we have 2 more points, which are more accurate. And we have just gone from having initial left knee point to having a left ankle and a left hip point. We can then go and do the same thing and have, go towards the shoulder and fine tune it, go towards the elbow, forward, fine tune it, and so on, until we have the whole pose parsed. And we have a series of key points which are clusterized into one single person as a separate entity from the other persons, from the other people. So we can just then go again, go to the second largest key points in the whole thing, and continue, and so on, and so on, and so on, until we have the whole poses parsed just by using tensors in a bottom-up way, which is quite simple. And this is basically Person Lab. It's a bit simplified. It has a lot of filtering and things going on, and it uses a huge transform for some things, but it's basically this. And but okay, now the important part is how was building this using Swift for TensorFlow. The experience had some good things and some bad things, but luckily the good things were the important things, like the design of Swift is really great. The design of the TensorFlow API is also really awesome. And the bad things, luckily again, are kind of things that are just work in progress that should be fixed with time. So the tooling is a bit incomplete. It has some bugs and so on, but the overall experience was very positive. So I'm just going to start like numbering a random bunch of good things and bad things like I did in the article. And the first really good thing I liked was the Swift type system. I just been using Python this whole time. So it was my first time using a very statically typed language, which I really enjoyed. And I'm going to show the 4 structures I use to build the decoder as a way to exemplify how the type system in Swift helped me write concise code, which was quite easy to read and fast. So the first structure is super simple. I needed to encode the concept of going forward or backward in this graph of poses. And I could have used a Boolean and just go is forward or is backward, but I chose to use enums, which I think are more descriptive. And when something fails, and you see forward or backward, you know what's happening. If you see a Boolean, you don't know if the Boolean means forward or if it means anything else when something fails or crashes. So okay, that's the first thing. Quite simple. The second thing is I wanted to have a way to access the indices on my heat map matrix in a principled way, like in an easy to read way. And for that, again, because one layer could be left eye, the one could be right shoulder, and so on. It's 17 key points, so I had to do it some way. And again, I use a very simple enum to just describe all my key points and how they index this heat map. So when something fails or something, I know that what key point was the culprit. Like for example, one time I was trying to join an I and an E, and I realized it because I could see the enums. If I just had seen the number of the index, I would have never guessed it. So it helps with debugging sometimes, and it's kind of clearer to just read the code. Then something a bit more complicated, I had to encode the concept of having two graphs with directions and a very particular configuration. And for this, I chose to create a function, which is called get next key point index and direction, which takes as an input our enum, our key point index enum, and it returns a list of tuples with each tuple containing a key point index enum and a direction enum. And the idea is that I can just go to jump some key point, put it as an input, and get the next key points, so I can just go and follow the parsing of each pose. And let's say, for example, I take as an input the left eye. Well, I should get as a return, I can go to the nose, going backward, or to the left ear, going forward. So I just write a switch statement, which in the case of left eye, tells me you can go or to the nose backward or to the left ear forward. And the beautiful thing here is that Swift has very good type inference, so I can just not have to write the whole key point type dot left eye, the whole enum direction dot backward. It just knows that if my input is of this type and my output is of type list, tuple, and enum, it can parse the whole thing and allow me to just write dot left eye, dot nose, dot backward, and it knows that it's supposed to be a list of tuples of enums. So that's pretty smart by the Swift team. And yeah, we can just go and do it for every single key point. And we just encoded the whole of the two graphs with the directions and everything into a single switch statement, a single function, which is quite fast because it's just enums on a switch statement, so it's constant time, it's super efficient. It's very clear to read, it's very concise, so I really like that. Okay, and have then the last structure we need to build the whole decoder. And I needed to find a way to, parting from both my key points and my direction, to go to the correct index on one of these displacement matrix and find the correct displacement. Now, I have 16 pairs of key points, and both the matrices share the same way of indexing. So if I go left eye to left ear or left ear to left eye, both matrices share the same index. I just have to choose the correct matrix. So I chose to use one structure for both matrices. And the way it works is first, of course, I just use the forward enum to choose the matrix. So that's it. But then I have to choose with some way to have a pair of key points whose order doesn't matter, and to use this pair to index the correct matrix in either one of the tensors. And for that, I chose a dictionary, which uses a set, so the order doesn't matter because it's a set of key points which maps to an int, and the int is the index of the matrix. So it's quite simple. I just write every single pair of key points with no regard to their order, nose left eye or left eye nose, and it maps towards some index in the matrix. Now again, the type inference in Swift was really great. It knew that I was supposed to use a set of key points as a key. So when I wrote my key, it just let me just write set and not write the key point index type every single time. And yeah, just by using these four structures, which are quite easy to read, I could encode the whole thing and encode the graphs, the access to each key, to each tensor. It was quite easy. So I think the biggest thing here is that it's easy to read. I mean, for example, using a dictionary to access an index is not super efficient. Having to do a hash function to access an index on a tensor is not super efficient. But it doesn't really matter in practice. It's the same basically, and the code is super readable. So I take it as a win. And the type system really helped me, I think, to build something easy to read and quite fast. Okay, the second part I really liked was the easy memory model in Swift. Swift really wants you to use pilot types as much as you can. And the Tensorflow API uses pilot types for mostly everything. So you can just use pilot types, assign them to functions and to variables, and just not think about it. And Swift is very smart and uses copy on write to avoid making too many copies when you're assigning things everywhere. Or maybe just do the copy when it really absolutely needs to do the copy. And also when something ends up on the heap, it uses reference counting, which again lets you have not to think about memory and just everything works and you just go ahead. I think this is kind of the biggest thing to take away from this presentation, that I could just write code in Swift without thinking about memory at all, at least when doing something like this, like TensorFlow. And it was fast enough so that it doesn't really matter how fast it is. And by that, I mean that I have two parts, a backbone and a decoder. And the decoder was so fast that it didn't really matter how fast it was, because the backbone took most of the time of inference. So for example, if I had written this using Swift or using just very carefully made assembly, it's basically the same, because the time it takes to do the decoder is negligible with regards to how the backbone works. And that's what you want. You want to spend the least amount of time writing the code so that it's fast enough so that it doesn't matter how fast it is, basically. Okay, and the last good thing was the TensorFlow API. It was really nice. I used to work a lot of TensorFlow 1, which has a functional style, and it has like a global state with your parameters, which is quite harder to use. But I always liked the PyTorch way of doing things, which is just taking a class, and the class means your model or your layer, and the methods are the operations, and the parameters are the internal states of your layer. And luckily, the Swift team did the same thing. They use structs for the layers and for the models, which look like this. You have, for example, the person lab heads struct, which I used to get the 4 tensors, is like this. It has 4 convolutions, and I just write each one, then go to and write an init function, which takes my checkpoint loader and loads on each layer its weights, and then just finally write the method that ends up running, which is called as a function, and it just runs my input through the operations, and everything's very simple. And this is very similar to how PyTorch works, and I think it's awesome. So yeah, very good. 1 second. Okay, now the first bad thing is that Swift is still very new. So some structures are missing. I couldn't find a binary heap, which I needed to sort things online and just get them in and out while I was parsing the key points. And so I had to just go and search for it on Google and just copy the code and paste it inside my repo, which was kind of unnecessary, I think. Yeah. So the second thing was I couldn't use tuples for code which was differentiable, and that's because tuples are structural types, so they can't conform to protocols, so they cannot be differentiable. So for example, I wanted to use a tuple to get the results from my forehead layer, and I couldn't, so I had to create a one-off struct to save the 4 results, which is a bit, it's a bit of it's a small detail, but it bothered me a bit. And the last thing was I couldn't find a way to create a fixed length stack allocated list in Swift. I had to use a dynamic array which gets on the heap. And as I have 17 key points, I wanted to have a fixed 17 length list for my key points, which could go on the stack and save me having to pay for reference counting and so on. But I couldn't. But again, this is very nitpicky. It doesn't really matter at all in reality. But I couldn't do it, so it was a bit of a bother. Okay, the bad thing number 2 was that I really missed the Python debugger. I couldn't just write, Python set trace and just start trying code away. I had to try the LSDB debugger, which was a bit more cumbersome to use. Had to run it on my executable, get the correct line or get the correct function and just try. And for some reason, I couldn't get it to work on structs. I couldn't access the self object from inside a struct method. So I couldn't really use it at all. I don't know why I couldn't, but I couldn't. So I just ended up using print statements to debug, which was a bit slower. Then I used Beam to write code. And about 2 months ago, I tried the language server, which Apple is building. And it was very hard to use. It's gotten much better recently, but it's still a bit slow. So you just press tab to autocomplete, and it takes like 1 or 2 seconds to autocomplete. But again, it's a bit nitpicky. It's a small detail. I had some bugs with the package manager. When I added a dependency for my project, it kind of created a local cache of the repo, and it didn't update when I built this again. So I had to nuke the whole thing several times. I never got it to understand what happened, but I had to just nuke the whole thing like a bunch of times when I built my package. Then I had, the first time I built the decoder, it was much slower than Python, like 100 times slower than Python. And that's because I was, on each access to a tensor, I was triggering a GPU to CPU copy. And that's because in its current state, the TensorFlow Swift runtime has this problem, which is getting fixed, luckily. So I had to create a wrapper and wrap each tensor and create a flattened version on CPU and create a custom way of accessing the index and so on. But yeah, after this, it was much faster, so it was okay. But yeah, it's just a small bug to fix. One more thing, when something failed on the TensorFlow eager side, I didn't get a stack trace. I only got the end of the stack trace, so I didn't know where the issue started from in my code. So I had to go and just try everything till I found what was triggering the error, which was slow. But yeah. And finally, the last thing, the ecosystem is a bit sparse. I wanted to create a demo which would take a webcam and get my image on it and just draw on the image the poses. And as I couldn't access OpenCV, because OpenCV doesn't have a Swift API, I had to go to a community project, which is called SwiftCV. And I had to add the functionality to be able to pick up a webcam and get the GUI going and get the drawing going. So I had to go to the OpenCV repo, look at the C++ code, try to wrap it in C, wrap it in Swift, build the whole thing, import it in Swift, and make it run. So I spent like, a day doing like this whole thing just to get the webcam and the drawings going. But it worked, so, it's okay. And yeah, just to end up my part of the talk, in the future, we want to get this repo, this personal post estimator, merged, if we can, into the official TensorFlow Swift model too. So that's great. And just to end up the talk, I'm going to show how it looks on a video. Due to the coronavirus, the office is empty, so I had to use a mannequin to get 2 poses on a video. So it looks like this. It's just me using the webcam and getting the pose of myself and of the mannequin going together. And it's, it works quite well, I think. And yeah, that's it.
If you can explain why we had a mannequin on the office, please.
Well, Ernesto really likes mannequins, so our office is full of mannequins. It's hard to explain, but we live with it every day, so it's fine. Okay, so now for the next part, Ian will show how the performance we got on the project.
Thanks, Al. I think you have to stop sharing your screen in order for...
Yeah.
Okay, guys, so I'm going to be talking a little bit about performance or more so about backends, I would say. There's not much to say about performance in particular for a couple of reasons. Of course, I'm not part of the Swift for TensorFlow core development team, or I haven't even contributed to it at all. So anything I say may be wrong, and I'm hoping they can actually correct me in case that is. So what I'm going to be talking about is first, I'm going to be talking about the cases where CPU times matter. If you work on AI, most of the time, what constrains you is GPU times. So you're not that worried about what's going to happen with the CPU. But there's a couple of cases. One of those is the person lab model we are doing here, we did here, that for which CPU times actually matter a lot. And I'm going to be talking about another case where that happens. And that's the cases where a project like Swift for TensorFlow, in my opinion, can really shine. The second thing I'm going to be talking about is about Swift for TensorFlow backends. And I'm going to explain what that means in case you don't know what a Swift for TensorFlow backend is. And if you haven't heard of X10, which is the next thing I'm mentioning here, I'm also going to explain what that is and etc. And finally, I'm going to talk about what happened when I tried to make Person Lab work with X10. Okay. So the first thing is, when do CPU times matter? And we are going to be talking about Alphago and about Person Lab. And when I say Alphago, I mean, for the people who know what Alphago is, which is probably most of you, I'm talking about the first Nature paper, which is more or less the version that for Diesel. For the people who don't know what Alphago is an AI developed by DeepMind that plays the game of Go, which is this I'm showing you right here. This is a game between Kobayashi Koichi and I think Lin Kai-ho in 1993. So the game of Go is a strategy game, and it's a turn-based game, and you place stones on a board. And that's all I'm going to say about the game today, because we don't have that much time, but it's a very interesting game. And if you want, and we'll talk about all the Go API, all the Go AIs that have been developed in the last few years, you can probably bother Alan to let me do that as well in the future, but not today. So the original Alphago architecture had a very typical architecture for this kind of problem, which is generally when we're working with board games, strategy board games, and turn-based strategy board games, the traditional approach is to have some kind of form of evaluating a position, of telling whether a position is good for a certain player or not, right? And also having some way of looking into the future. So saying, okay, how good is this position going to be if we play this and they play that and we play this, etc. Right? In the case of Alphago in particular, we had the value net, and that's a convolutional neural network that's used exactly to evaluate a position and tell you how good it is as a percentage. So it says, okay, I think in this position, white has a 70% chance of winning, for example. And we also have a policy net that tells you, given a position, which moves are likely. So the only thing that PolicyNet does is say, hey, I've looked at a lot of positions. PolicyNet is trained in a supervised fashion in the first Alphago. In this position, I think these are the moves that you are likely to see. And based on those two things, we actually have to do a Monte Carlo tree search. And what's interesting about all of this, and I'm sorry, I'm going to drink some water. And what's interesting to me about all this is that the tree search needs to happen on CPU. And in that kind of case, this is not just some computation, it's pretty intensive. So in this kind of case, what you would do normally if you're working with TensorFlow on Python, or you're working with PyTorch, is you would write the tree search on C++ or on C. Because writing it in Python, where it's custom code that doesn't really use as much of C code, because sometimes when you have CPU intensive code, you can just call NumPy or call SciPy or call scikit-learn, and you're just going to be running C code anyway. But in a case like a Monte Carlo tree search, for the most part, you're going to have to be writing custom code, and it's really going to be constrained by you having to use a Python interpreter instead of C++. So this is the typical case where a language like Swift that is fast out of the box on CPU can actually help you have a much cleaner development process where all the policy net, the value net, and the tree search is all written in the same language, and you don't need to interoperate between Python and C++. One thing that's worth mentioning at this point is that Swift is not the only project that's trying to get something like this. There's also very similar attempts at getting this on the Julia community. I personally don't know much about the Julia ecosystem currently, so I'm not going to be talking about that, but it's worth mentioning that that's another possibility which you might be interested in finding out about. So this is Go, Kobayashi Koichi, etc. And we also have the Person Lab architecture, which we have already talked about. You have a convolution, and that runs on a GPU. And on the other hand, you have the decoder, which Lalo talked about, which runs on a CPU. And it's the same thing. In the case when we wrote it on Python, we wrote it all in pure Python because I didn't write it actually. When Joaquin wrote it on Python, we wrote it on pure Python because we didn't care about performance as much for the use we were giving it. But if we did, we would have had to rewrite the decoder on C++. And that would have been comparatively annoying compared to having to write it all in a single language. Okay, and this is the same Go game, but analyzed with Person Lab. And now that's essentially what I wanted to talk about. There's certain cases in AI where actually CPU times matter, and they matter as much as GPU times. And in those cases, it's really interesting that in these last few years, we've actually started working, not me personally, but the community has started working on getting languages that are good on CPU and are also easy to program in and suitable for machine learning. So when I say Swift for TensorFlow backends, what do I mean? Let's first talk about something else. What is XLA and what is X10? Okay, X10 is one of XLA or X10 is one of the Swift for TensorFlow backends, but I need to explain this before I talk about backends. So XLA is, you can think of it as a part of TensorFlow, although at this point it's also used not only in TensorFlow, but also in JAX, I think. But in any case, it's a way of compiling a graph from your TensorFlow code that can also be optimized, and it can run on TPUs and GPUs and so on. Okay, it stands for Accelerated Linear Algebra. And in general, it's useful for speeding up your code in a lot of cases. All right, so XLA is not the default TensorFlow backend. Normally, when you run TensorFlow, you're not running XLA unless you want to run XLA and you do it on purpose. And it's also not the default backend when we run TensorFlow in Swift for TensorFlow. Okay, not currently at least. The default backend would be the TF-Eager backend. And the TF-Eager backend, if you know TensorFlow, you've heard of TF-Eager, runs a single operation at a time. What that means is that if you have some graph and you first need to do an addition, it's going to tell the GPU, okay, please do an addition. And the GPU is going to say, hey, I've done it. So to explain this chart a little bit more, you normally interact with the CPU directly, and you only interact with the GPU indirectly because the CPU tells it what to do. So in this case, when you mention some operation, the CPU is going to tell the GPU to do it, and the GPU is going to say, okay, I'm done. And then the CPU is going to do something else, and the GPU is going to say, I'm done. What's the advantage of using XLA instead of the TF-Eager backend, which does this? Well, XLA can do this sort of thing where you say, hey, please do an addition operation and then a product operation. And after the GPU does that, it's going to say, okay, I'm done. And the important part of this is having the chance of scheduling both operations at once also gives you a chance to optimize how those operations are scheduled. And it can also allow you to fuse the operations. And all of that can give you a huge speed up in many cases. So up until recently, very recently, Swift for TensorFlow only used the TF-Eager backend, and in many cases that meant it was slow on GPU. Right now, I think maybe today, we had the first more or less stable release with X10. And X10, what it does is it's just the part of Swift for TensorFlow that makes it so that you're able to use the XLA backend. So it compiles everything to XLA and it handles that. Okay, so it's so new that it's actually something that came out today. We were working with a release candidate since Monday. The release candidate was released on Monday. And before that, we were working on nightlies. So this is all really new and changing fast. So anything I say about X10 might be false in a couple of weeks or maybe even today. Okay. So in any case, the idea with this is once we have X10, we can use the Excellet backend. We can make it so that Swift for TensorFlow has the niceties of a TF figure backend. So the API is nice. That's essentially the most important part. The API is nice. And you can also use your normal for loops and etc. to write your code. But also the niceties of an Excellet backend that essentially runs faster. So I was tasked with migrating in a way our code to X10. And I thought it was going to be a long process or a hard process at least. And it ended up being almost ridiculously simple. So what happened was I have my code. I have all of the code that works for Person Lab, and it worked on the TF figure backend. So the first thing I did was I went to the main file and I added a line that defines a device, right? And this device says, okay, the kind of device is a GPU. The ordinal is 0. This is just the normal CUDA ordinal. So if you have more than one GPU, you may write 0 or something else. And I have to say what the backend is, which in this case is going to be Excellet. I define this GPU device, maybe on the global scope or whatever. And then I need to add this, which is at one point we defined our models. I just need to write .move to the GPU device. And in this case, I only run it if we have a flag set here. And any model you write just supports move pretty much automatically. I know there's some exceptions, but in principle, that's how it works. And that means that it was really, this was pretty much all I had to do in order to move our model to X10. After I have this code, our model is running on X10, it's running on a GPU, and it's using Excellet as a backend. Okay, so that's pretty much easier than I thought it would be. The only hiccup I would say is this part, which is the lazy tensor barrier. In some cases, you need to add this in order to tell X10 to evaluate things immediately. So X10, in order to be able to do this, let's go back, Excellet backend sending multiple operations at once. X10 actually collects all your operations lazily and then runs them when you actually evaluate a result, okay? So if you need to evaluate a result in a way, but you don't have any actual evaluating operation, you need to add a lazy tensor barrier. For example, if you're training, you will need to add a lazy tensor barrier after each training step. I don't know if this is going to be part of the X10 API in the future, but it is now, or it was yesterday at least. But this is the hardest part, okay? So I didn't have to touch the actual code of the backbone. I didn't have to touch the actual code of the Person Lab heads. I just had to add 2 move operations that were really simple to understand. So I really like the API, and I was actually expecting something much harder. And I think Lalo was as well, because he tasked me with this as a big task. Okay, move the thing to X10, and I was done in 10 minutes. So that was really impressive. Apart from this, the other thing I wanted to talk about is, okay, but does it run faster? And our model in particular is not the best example to switch to X10. The main reason is, if we go back to these things I have here, when you have really small operations, the difference in having to schedule them one after the other might be big, because the time it takes to do a simple addition on a GPU is really small. So the time it takes to schedule it can be big compared to that. But here, if we change the sum and the multiplication for just for a big convolution here and a big matrix multiplication here, then the scheduling time is too small compared to that, and the difference is not going to be as big. There's another thing with TF figure, which is more general, which is TensorFlow was written not to have an eager backend, but initially to have this graph backend that's declarative in nature. So TF figure was written as a way to make that existing backend work in an eager way. And that has a lot of, let's say, legacy stuff. Let's just say like that. So that means there's a lot of inefficiencies that are created by the fact that you need to use the existing TensorFlow backend, but make it work in an eager way when that wasn't the initial idea. In our model in particular, we only have a couple of really big convolutions. That's all the model. And that means that fusing them is not really possible, and scheduling all at once instead of one at a time doesn't really help that much. Still, we got a small improvement in time in the convolution. And as you heard Joaquin mention already, we also had a small improvement in time, or it wasn't that small. We had like a 1.5 times improvement in time in the decoder, but still the end result was about as fast as it used to be. And the main reason is because actually in the middle point between the two, when we are moving our tensors from the GPU, which the convolution uses, to the CPU, which the decoder uses, it was actually slower on X10 than it was with the TF-Eager backend. And those are small hiccups that I assume are being worked on, and etc. As I said, this is really new. This came out literally today, and we were using a non-stable version, which we were using a release candidate. So all of those details, I wouldn't pay too much attention to until we actually have a more stable release, and this has been out for a couple of months, and etc. But the experience was really, really nice in the sense that the API was really easy to use, much easier than I thought, and much easier than I'm used to in PyTorch and in TensorFlow in general. Even just saying, okay, I want this to run on one GPU and the other, it tends to bring about certain problems. And in this case, it just was a couple of move operations, which surprised me. And that's all I have to say for today. I think we had scheduled a couple of questions now. I don't know what time it is and how much time we have.
Yes, and we have people from Google here. We have Brennan, who is leading the TensorFlow project. Sorry for not naming you before, and other people from the core. So we are going to maybe even give them the chance to speak a little bit about this and the project. And then while we are collecting questions from the audience, so whoever wants to speak.
Yeah, hi, can you hear me?
Yes, one of the 7 Brennans. Now we're a little bit less.
Yes, we had a bit of a snafu in getting all to join. I at least am not so familiar with Zoom, but first of all, I just wanted to say thank you so much for organizing this, for using for TensorFlow, for being an early pilot customer, a user of the tools that we've been working on. It's been fun working on them, on building out the tools and collaborating with other folks within Alphabet, but it's really awesome to see you all take them up and use the early release candidates and give us awesome feedback and make something that's really, really neat. Your observations at the beginning in a world where you're just doing most of your computation on the GPU and the CPU side is relatively simple, the existing tools and frameworks are absolutely fantastic for it. But we are starting to see in a number of areas that doing more interesting things with the host CPU is potentially a really powerful next phase of evolution in deep learning and beyond. There's been a fair bit of research at DeepMind. There's been research in other parts of Google, other parts of Google Brain, where we're starting to really see early indications that this is going to be really important. I think actually just a few weeks ago, Jeffrey Hinton's lab published a new paper called The Imputer, where they're doing crazy dynamic programming work. And that's been another inspiration. There's been sort of a handful of these models, and they're always very difficult to use. And unfortunately, I think we haven't seen as much follow-on work. And I think it's because we don't have the right tools available. And that's what Swift for TensorFlow is really trying to build, this next generation of deep learning infrastructure that can unlock the whole next wave of both algorithms research and applications. Right, one of the things that's really nice about Swift is it compiles down just like C, and so you can link it in anywhere you have C or C++, which is really a superpower. I find it's a fair bit more productive to work in than C and C++ as well, so that's convenient and important too. The last thing, I thought that it was really great that the Julia folks, I know actually relatively little, but I think Julia has been a very interesting community, and they've been doing a lot of awesome stuff in this space as well. And I have a hypothesis that actually Julia and Swift are potentially some of these next generation, where we'll see some of the next generation stuff happening. It's definitely want to echo that it's early days in building this out. We're really excited by some of the early indications we have, but it's still early, and so we're really looking for pioneers and contributors who are willing to help build this next generation. That's what makes things so exciting for us, and hopefully for you all, is you really are going to have the opportunity to shape and influence the people that show up, to shape and influence this next generation. So thanks so much, and I see at least one question.
Yeah, there was actually another one which was sent through the chat. Maybe we start with that one. First, I want to thank you, Brad, and all the folks from Google for joining and making this better than it would be without you. So, and thank you for shaping these tools that we find very interesting and for sure will be a part of how we do machine learning in the future, in the near future, we hope. So, Lalo, if you want to add on how people can find our personal lab model code and
yeah, I'm going to link it in the chat. We hope to get it merged into the Swift Zoo repo sometime in the future, maybe. But yeah, I'm going to link it. And today I saw that the differential programming feature got added to master on Swift. So congrats to the Swift team. That's awesome to hear. And yeah, I saw one question on the chat, which I think was addressed to me, which is if I ever needed to use the Python object from Swift for TensorFlow. I didn't use it at all, but I was very tempted to use it for the OpenCV parts. I had to choose between just going to OpenCV and grab the C++ code and so on, or just using the Python way. I did it on Swift because I just wanted to do the whole thing in Swift, but I would have probably just used the Python object of the Swift of the OpenCV Python library if I had to do it fast. So it's good to have the ability to use the Python part or just do it on Swift if you want. So yeah.
There's another question from Alexander Utsolev. He says, thank you for this great presentation. Can we say that using Swift for TensorFlow, we will not need to use some high-level frameworks like Keras, or is it something really apart? Thanks.
Dan, would you like to chime in here? I thought you wrote a pretty good answer.
I'm writing another answer, so would you like to talk instead?
Okay, sure. So one of the philosophies that we have, or I guess that I've imposed on the Swift for TensorFlow team and we're trying to use for the whole project, is an infinitely hackable platform. And what that means is that we provide high levels of abstraction that can get you started and get you going really easily, that you've got a bunch of functionality in the box, all the smarts from the greatest research is easily available. But one of the things that is so exciting about a platform like Swift is that because you have a fast host language, you should be able to customize and change anything, and you should be able to do it inside a Jupyter notebook or inside a Colab notebook. And so we're working on providing a stack of APIs all the way down to the lowest levels. Our goal, again, is an infinitely hackable platform where you can customize and write custom models, custom training loops, custom layers, but also even custom kernels is our eventual goal, and be able to do it all right in a notebook and have it all fit together seamlessly. And this is because I think that research is all about pushing boundaries and doing experimentation. And the only way you're going to be able to answer all the questions you can think of asking is if you have an infinitely hackable platform. This is absolutely necessary for high quality research, I think, over time. I really like the metaphor earlier, and I actually use a similar one of, we often look under the street lamp. We look for our keys under the street lamp. And we really want to shine a floodlight on a much larger swath of area with next generation technology. But I also think that infinite hackability and customizability is just as necessary, not just for research, but also for production and real applications. That's because although research is incredibly hard and you have to ask all sorts of questions and try all sorts of crazy things, production is hard in a very important and different way. But having customization, the ability to slot in higher performance optimizations or being able to fit into an existing system or just to deal with the realities of your environment, you often need to be able to customize and customize it efficiently. And so, the question, getting back to the question, using TensorFlow, you will not need some high-level API or framework like Keras. You don't need one. We hope to provide a really good one. In fact, we hope to provide many levels so that you can use it if it's helpful for you, and you can customize it or write your own just as easily and have it be just as good if your needs don't fit.
Thank you for your answer. Maybe another question for the Google guys. Hot question: what are the future plans of Alphabet for Swift for TensorFlow? Is it a toy project, or is it going to be further investment on it? And what's the best ways to contribute to models?
Fantastic questions. Google's a complicated and amazing space for now. Let me actually just start with acknowledging the elephant in the room, and that is Google's very good at making amazing technology and abandoning it. I still have my heart broken over Google Reader. So this is an important reputation that is, I just want to acknowledge that exists. Google as a whole is trying to break that reputation. That said, and so as a result, Google is trying to be very careful about what is a supported product and what is not. So for TensorFlow is not an officially supported product in the way that TensorFlow is. It's still early stage, but again, we're starting to see really exciting indications, and the more the community uses it, and the more research discoveries that we have, and the more applications that are built on it, that's setting everything up for success. So I don't want to set the wrong expectations that Swift for TensorFlow is guaranteed to be around in 10 years, but TensorFlow has been a huge success for Alphabet, and JAX and Swift for TensorFlow are coming along in that same vein. And so, these decisions about what's the long-term path don't come down to me, and so I'll just try and be as upfront and honest as I can.
And how can people contribute to models?
Yeah, so,
I can actually...
oh yeah, Brad, please, you'd be way better.
You mean to step on you there? So that's kind of that's important to me. And this is also something that we just had somebody ask on the mailing list this morning. How can I get started with the project? What's a great place to put in a first contribution? We have an active repository of Swift models at TensorFlow/Swift-models. Where we have a number of example models of a variety of types, and we're looking to expand that to different types and classes and so forth. Working with a Person Lab model, for example, like as it's been developed, that's been really very interesting to see, because it was a different class, it was a different kind of structure from some of the models we had, so it was exposing like different performance edges and so forth. And that's what we're trying to have is a good set of reference models, but for both people to learn from, but also so we can use it to benchmark and see like what our APIs need to have, or how they could be cleaned up, or things of that sort, like really trying to dog food our own technology there. And so that's a great place to start. We have an open source repository with these models, and we've identified a number of like starter issues where, hey, we've got a few things we'd like to get cleaned up. You can step in and work with that. We've also identified models that we'd love to have in there, things from like speech generation and other like benchmark models. We're working on things like object detection and so forth to go and have those models added in there, as well as like a lot of benchmarks around that. So we've identified some good like starting places, some models we'd love to have in there. And we really appreciate any contributions there. It's a very active area for the community. We have a lot of people that have done that. I think Ava did a survey of the models that have been contributed in the last year, and something like 60% had been contributed by the community, which is really awesome. And we love to see that. So that's a great place there. I'm very active there, so it's near and dear to my heart. And so we'd love to see any contributions there. And again, if you have any questions, we have an open mailing list. Please feel free to ask us about what you want to have there. We have open design meetings generally every Friday. I think we're going to have one tomorrow. So please feel free to stop in and attend those. And we'd love to point you to ways to get started.
Thanks for that. If there's another question, maybe for Lalo and Ian, can you comment a little bit more? Where is the performance difference between Python and Swift comes from? Was the only bottleneck the decoder in the case of Personal Lab?
Yeah, basically a convolution done in Python or Swift or whatever, they all use very optimized CUDA kernels, so they all run basically as fast, especially in the case of such a simple backbone as in Personal Lab. But the difference was the decoder. It has a lot of accessing tensors and just iterating over each single pixel. So in the Python version, the decoder and the backbone were the same time. So each one took half the time of an inference step. In the case of Swift, the backbone was slightly slower than the Python version, just because the Swift backbone is a bit new still. But the decoder took basically 0 time, like it didn't count towards the inference time. So it was twice as fast, the whole thing, just by using Swift. And that's just because I use NumPy in Python. I try to do it correctly, but still there were a lot of accessing each pixel and for loops and so on and so on and so on, which Python really struggles with. So that was the main difference.
Thank you. Are there any intention to build tools similar to Pandas, Task, other libraries necessary for data science work? Great question. Maybe someone from Google knows something.
Yeah, so the Penguin library, I think Pandas is an amazing library, and pandas are great, beautiful creatures, but somewhat large and slow. And so if we Swiftify it, I thought we'd come up with a penguin, similarly formal looking. Anyway, that's the metaphor behind the name, but we have a library called Penguin that I referenced earlier on the chat, where we're working on a variety of data structures. We have a early heap data structure, and we have early pandas-like functionality, data tables, and beyond. The goal is absolutely to go in the direction of distributed data tables. We're going to build up the abstraction slowly and carefully, but absolutely, that's already in progress, because we've seen this is necessary and important for internal usage of these Swift for TensorFlow and libraries within Alphabet. Our goal, we want to try and have things be as open source as possible, and so we're developing that library fully out in the open. Yep, absolutely. There's been some great work by previous Google Summer of Code folks, such as SwiftPlot, and there's also a plotly.swift that was contributed by the community. The SwiftPlot stuff was done by Google Summer of Code volunteer. Brad can perhaps talk more. That was sponsored by Google.
Yeah, and that was a good example of, like, we saw like there's a little bit of a gap there. Matplotlib is fantastic in Python, used everywhere. And so, like, okay, can we do something in Swift that also is as cross-platform and can be beneficial not just for like a data science ecosystem, but it really has taken on a life of its own. The latest contributions to SwiftPlot, like I think during the Google Code-in process, folks added capabilities such that it can even run on an Apple Watch. And so it's like scaled down to that level of a platform, be able to do that, have it in iOS applications, be able to have, in other mobile contexts, as well as being used for data science. It's a great example of, like, we saw a little bit of a need, and then a student was able to do fantastic work to make that work. Karthik Iyer did incredible work in building that up from scratch into a component of a data science ecosystem.
Thank you for that. So I think that in the interest of time, we should stop here. So thank you all very much for being a part of this. It was truly great, surpassed our expectations completely. And we are really happy to be on board this Swift for TensorFlow ship. And let's see where it takes us and where we can help it sail. So thank you all very much. Thanks to the attendees, to our clients in the audience, and to everyone. The recording will be made available, and we will tweet things about this with the takeaways from the webinar soon. So thank you all again for participating. Bye.
Thank you.
Bye, guys.
Thank you.
Bye.